Okay, everybody. So I wasn't here last week. You guys know that. We had Zico Coulter come and give the lectures last week, and I heard he did a really great job, so I'm very happy about that. Before I move on, I wanted to address what happened a week ago Saturday. I was actually here in Pittsburgh when it happened, and I wasn't able to be here the next week. I had already planned to travel. I just wanted to say that, like everyone else who's been telling this to you, I think it's just a horribly sad and terrible thing that happened. And my thoughts are with everybody who was affected by this, directly or indirectly. And if you found it, it affected your work last week in any way, please come talk to me. I'm happy to make accommodations. So just come and talk to me, and if you felt like it was a rough week for you, it's understandable. We can try to, make any accommodations. Even if you turn in the homework somehow and you felt like because of what happened, you wish you had an extra day or something but never asked for it, just come talk to me. We'll figure something out. Okay, so we are officially through the kind of basics in the course. So according to the course website, we've moved through algorithms 2, and I actually added something just this morning, like a little recap here. It's linked right here. And I don't really want to go through this carefully because I want to save the time for today's lecture, but you can take a look at this if you're curious. I basically tried to compress everything that you've learned so far into in like easily kind of referenced format. So something that you could look back at and just kind of get a snapshot or print out and like kind of whatever, put on your wall or something if you want to remember what you learned in the course. So we have gradient, subgradient, proximal gradient, stochastic gradient, Newton barrier method, primal dual and Cherry point method, and quasi-Newton, and the last one is proximal Newton. These methods, I think, I think they're staples of optimization and machine learning, but they're just more recent. So coordinate descent, 8mm, and Frank Wolf, we'll learn those starting on Wednesday. We'll learn coordinate descent. 8mm is the next week, and Frank Wolf after that. So I haven't filled these out yet. We can fill them out after we do it. And what the rows are here are what is the criterion that these methods are able to handle. So what are the requirements they place in the criterion? Like, for example, gradient descent assumes that f is smooth. Newton assumes that f is doubly smooth. I just mean two derivatives by this. What are the constraints it can handle? So gradient descent can project onto the constraint set. That's how it handles constraints. What are the optimization parameters that it entails? So for gradient descent, it's just the step sizes, and you can either fix it to be less than or equal to 1 over the Lipschitz constant, or you can do line search. What is the iteration cost? So this is just informal. This row, it's just I'm kind of talking about the kind of base case here, or the most generic case. Cheap for gradient descent, and it's going to be expensive for Newton. And the rate. What are the rates we'd expect in terms of getting an epsilon suboptimal solution? So there's 1 over epsilon, 1 over the square root of epsilon, etc. Okay, so just all that stuff compressed into like a couple of pages. Okay, so today we're going to talk about numerical linear algebra. You guys voted on retaining this lecture. I was thinking about axing it, but I think if you know it already, then hopefully you'll still kind of find that this is useful, because I'm going to try to cover, I guess, a lot, and maybe some that you haven't seen. And if you don't know it, then here you go. This is like your intro to numerical linear algebra. So starting today, I guess going through the end of the course, I'm going to try to cover probably a bit more in each lecture because they're advanced topics. At the same time, the only homework you have left, I'm writing now, and it's not going to be, I'm not planning to make it as hard as the previous homeworks, and we're going to be covering kind of, I think, harder topics, maybe trying to cover a bit more in terms of the scope of what we cover, but I don't think you need to understand things as deeply. This is kind of the nature of advanced stuff. Just being able to see, I think, a lot of advanced stuff is going to be good. So that said, this lecture, I'm not sure we can get to all of it, but I'm going to try to kind of pick up the pace a bit of the way through. So last time we talked about proximal Newton, Zico covered this. You can think about it as the analogy to proximal gradient, where you keep the full Hessian rather than, when you make an expansion of G, just use a multiple of identity times a multiple times the identity for the second order term in the quadratic expansion. Okay, so I make a quadratic expansion of G, but I use the full Hessian, and I keep H around, and I at every step I find the direction that looks best with respect to this expansion. Then I take a step in that direction by some amount, tk, where I use line search for it. Okay, the iterations are typically very, very expensive because this is a kind of a formidable optimization problem for generic G, and even for a nice H. It's a difficult optimization problem, and it usually requires an inner optimization, like running another optimizer just to solve this. The most common coupling with proximal Newton is coordinate descent. So you haven't learned that yet, but the most common coupling is to use proximal Newton and then to solve the inner subproblem with coordinate descent. And when we learn coordinate descent, you'll see why. It's because for quadratically regularized problems like this one, it can often be very, very efficient, depending on H, but for a lot of H's that we care about, it can be very efficient. And the upside to this, to having very difficult iterations in terms of computation, is that typically very few are needed until you converge. So it's local quadratic, just like Newton's is. Okay. So here's the outline for today. We're going to start from scratch. I'm going to tell you what a flop is, and we're just going to go through kind of quickly the flop count for a bunch of the basic operations that you would have encountered so far in this class, and also just generic things that you'll be encountering as you go through kind of any form of engineering or statistics or machine learning. And then we'll talk about solving linear systems, which is that's like our focus today. And we're going to talk about it via two ways. One is with direct methods, which invoke things like matrix factorizations to solve these linear systems. And the second way we're going to talk about is using indirect methods, which I'm putting at the end. But this you'll see relates more to optimization as we've learned it so far. And in the middle, I'm going to try to, actually throughout, I'll try to kind of give you a feel for why you might choose different methods for solving linear systems in different situations. So what is a flop? A flop stands for a floating point operation. And quite literally, we interpret it to mean one addition, one subtraction, one multiplication, or one division of floating point numbers. So if you're programming in essentially any programming language and you're using floating point numbers as storage, then for every addition, subtraction, multiplication, or division, you count one flop. It serves as a basic unit of computation, which is why we like it. And we're typically interested in rough, not exact flop counts, right? To say that something has, exactly this many flop counts is not typically useful, or it's probably it's probably too difficult to work out for most algorithms that you care about. So we're interested in flop counts in terms of asymptotic notation, like as a function of the input size n, how expensive are these flops? And it's not perfect either. If we're just talking about addition, subtraction, multiplication, division, then a for loop where I were to loop through the elements of a vector and set every element to 0 would cost 0 flops, right? Because there was nothing in that involved arithmetic operations. And clearly that costs something. Memory access and memory writing cost something. And we might think of this as actually being order n operations if we had a vector of length n. But in terms of flops, which is the standard in numerical methods, you're not counting that. Okay, we're just talking about arithmetic operations. So let's go through like the very basic stuff. Vector operations. If I have two n-dimensional vectors, addition costs n flops because if I'm adding a to b, right, then I'm adding every element to a to every element to b. That's exactly n additions. Scalar multiplication is also n flops. That's just exactly n multiplications. And an inner product costs 2n flops, right? Maybe everyone can see why that is. It's because I'm doing n multiplications, every element of a times every element of b, then I'm adding the resulting thing, the resulting elements, okay, which is probably actually 2n minus 1 flops, right, because I'm adding, no, that's n additions as well. Okay, but we probably only care the fact that these are all linear. That's all we really care about in this case, that they scale with n. Okay, so let's, this is again just the very basics we're talking about here to get you an idea of how expensive various things are that are common operations. How about matrix vector operations? So if I have a matrix A, which is m by n, and a vector B, which is n-dimensional, okay, how expensive is it to multiply A by B, matrix multiplication A by B? So for me, with every single one of these things, I draw myself a picture. I always think pictures help. Okay, if I have A and B, I want to multiply A by B. So I have to do per row, right? If I look at the first row of A, inner product B, right? That costs 2n flops, just like the inner product costs 2n flops. And I have to do m of those, right? One for each row. So that's why the total cost is 2 times m times n flops. And again, what we walk away with here is that it's of order m times n. That's how expensive it is to multiply a generic matrix by a vector. How about if A is S sparse? So that means A only had S elements that were non-zero. So here it has m times n elements that are non-zero in the most generic case. If A only had S elements that were non-zero, then you can convince yourself that the entire cost is just 2 S flops, right? Because in terms of arithmetic operations, I only have to ever do multiplications or additions for the non-zeros, and there are S of them. Okay, so the total cost is 2 times S. For a k-banded matrix, that means that I have a matrix that has only in each row a total of k non-zeros. Okay, that was a pretty bad drawing of a banded matrix. Let me try that again. In each row, let's say I only have k non-zeros. Okay, that's a special case of an S-sparse matrix where the sparsity is n times k. And I guess here I'm assuming a square matrix n by n. So the computation, the flop count for multiplication here is just 2 times n times k. So again, I think of it as order n times k. For a low rank matrix, this is where somehow you can save a lot if you are if you have a nice kind of factored form for the low rank matrix. If I can write A as an outer product of vectors ui and vi, and I have, let's say, a sum of r such outer products, then the total cost is 2 times r times n plus n. So you can work this out in various ways. One way is to think about, if I multiply by b here, then I have to take the inner product of vi times b, and you know how expensive that is from inner products. And I have to multiply that scalar by ui, okay? And I have to do that r times, and I have to add them up. And if you go through that calculation, it's just going to be 2 times r. And let's suppose that actually n was a was square. It would just be on the order of r times n. Okay, so if I have rank r, then I can, if I have factored form, I can do very quick matrix multiplication. And this is again where somehow flops aren't perfect. For a permutation matrix, the cost is 0. Why is that the case? What would I do with a permutation matrix? I would just, I'd swap elements of B according to the permutation. And there's no arithmetic operations there. So the cost, according to flops, is 0. But maybe, like if we think about a more general notion of operations, I would think that it would be n. Again, it would be order n if we had an n-dimensional vector. Okay. So some more things. Matrix products. If I multiply two matrices, let's say an m by n matrix by an n by p matrix, then in general, okay, we can go through this calculation just like we went through this one, though now we have to multiply by p because we have to do it, let's say, for multiplying a by b. Then I have to, for every column of b, do the multiplication by a. And we know how expensive that was. That was just 2 times m times n. And if there were p columns, then it's going to be 2 times n times p. Okay, so again, if all the matrices were square, so if both matrices were just n by n, then this is going to be in the order of n cubed. So it's actually a very expensive thing to multiply two dense matrices, at least if we're thinking about doing so in this kind of generic way. If A was sparse, okay, by the same arguments that we used to get to this case, multiplying A by B is going to cost substantially less. It's just going to cost 2 times S times P flops, where S is the sparsity of A. Okay, so if S was a constant, let's say S, like I had constant sparsity, or even if I didn't have constant sparsity, let's suppose I had linear sparsity. If S was n, this would be in the order of n squared for square matrices, which is substantially cheaper than n cubed. And it's also less, of course, if B is sparse. So multiplying 2 sparse matrices is a very cheap operation. Now it depends on how much the sparsities overlap. Right, that's going to be the resulting cost. For matrix vector, okay, this is a case where you could think about it in different ways, and you can be sure that every programming language that you would program in, like I would assume this is the case in like literally every programming language that is written to do matrix operations, does this properly. So it does the association properly. So for example, if I were to first multiply A by B, then multiply the resulting matrix by C, that's going to be more expensive than I need, right? It's going to be on the order of n cubed, because that's going to be dominated by, for square matrices, by the multiplication of A by B. If you first multiply B by C and then multiply A by that resulting vector, or take A times that resulting vector, then it's on the order of n squared, because it just costs 2 matrix vector products for square matrices. So if you didn't use any parentheses, and I think any programming language is going to know to somehow do this association in the right way to save on computation cost. Okay, but those are somehow like just basic reviews. So all the simple stuff you do with vectors is order n. Matrix vector multiplication is order n squared. If things are dense, it's much cheaper if things are sparse. Matrix multiplication is order n cubed. In general, if things are dense. That's the highlight. Solving linear systems. So this is where things get more interesting. I mean, there is actually still, to be honest, research being done on even matrix products. I know that people are looking to kind of push the limits of how fast that can be done. But I think of that as somehow more of a theoretician's interest, to be honest. Solving linear systems is where things get really interesting, because it's something that I think we all take for granted. You guys, if you use MATLAB, you just call A \B, and you have no idea what happens, but something happens that's fast if A is sparse. And it's slower if A is not sparse. And, you know, I think that's probably that actually describes most of us in terms of our interfacing with solving linear systems. But there's a lot of intricacy here in terms of how we solve linear systems and how we deploy various algorithms to solve particular linear systems. And it's relevant to our course because the general principles we see here, like when it's slow and fast to solve a linear system, that will guide us maybe as to when we may or may not use Newton's method, because the core operation in every call of Newton's method is to solve a linear system, right? I have to solve a linear system in the Hessian to get the search direction. I have to solve this linear system to get the search direction v, right? So I can think about this as like A times v equals b. And, you know, again, so far, at least in this course, and I think most of us in our day-to-day, you know, experiences, we just kind of ignore the fact that this is actually not a trivial thing to do. And that's what we'll talk about today. So in general, okay, this costs n cubed flops. That's the most general case if A is dense. I'll explain to you kind of where that comes from and all the methods that achieve that. Or not all of them, but let's say the common ones that achieve that. And I just wanted to note that for a dense matrix, that's as expensive, okay, as doing a matrix product. Okay, so solving a linear system, doing a matrix product for dense matrices, they have the same kind of scale in terms of, let's say, asymptotic notation. They're both order n cubed. What about some special matrices? So there are various special matrices that actually have a nice structure and enable us to solve linear systems much faster. And you may think that it's kind of silly to point out, you know, for things like diagonal or permutation or triangular, but actually this is the basis for all of matrix factorizations, essentially, is recognizing these simple cases. So that's why we're going to go through them kind of carefully. So for a diagonal matrix, it costs n flops to solve a linear system, right? Because if A was just a1 through an and all zeros, and I asked you to solve ax equals b, then you have to just solve ai xi equals bi for all I. That just requires n divisions, right? So that's why it's so cheap. For a lower triangular matrix, so that's a matrix that only has non-zeros below the diagonal, so the diagonal and below. So maybe this is all non-zero, and that's 0. Okay, it's on the order of n squared. And that comes from a method called forward substitution, where we just solve, let's say, the very first component of our system of equations. So because we only have one non-zero in the first row, I just have a11 times x1 equals b1. And so the solution is just requires one division, b1 over a11. And then the second row gives me the equation a21 x1 plus a22 x2 equals b2. But I know what x1 is. I just solve for it, so I can substitute in. And I'm substituting in a forward way, because I'm always substituting in the next component of the system of equations. And I can solve for x2 directly, and that gives me this. So there's an exact form I get for x2. And then I substitute in for x1 and x2 in the next component, the third component, and I can solve for x3 and so forth. Okay, and that costs order n squared flops, because let's say in the last line, I'm doing, in the last line alone, I'm doing n flops, right, to compute xn. And the previous line, I'm doing n minus 1 flops. And the previous line, doing n minus 2 flops, etc. And the sum of the numbers 1 through n is on the order n squared. Right? It's n times n plus 1 over 2, which is on the order of n squared. So we think about this as being substantially more expensive than diagonal, but substantially less expensive than a dense matrix. For an upper triangular matrix, so it's the opposite. I have non-zeros just on the diagonal and above, and I have zeros all below. It's the same idea, just in reverse. It's called back substitution. It's again order n squared. Let me tell you about some other matrices. So some of these will be easy to see, some of these not. And some of this is the topic of current research, and hence is not even really well understood. For an S-sparse matrix, okay, solving a linear system often costs much, much cheaper than n cubed flops. But somewhat, I think, maybe surprisingly at first, given the fact that it's 2018 and we've been solving linear systems for I don't know how many hundreds of years. For a long time, people have been thinking about this, at least 100 years, in some form. It often is the case that we cannot describe exact worst-case flop counts for sparse linear system solves. Okay, I'll hint at that a bit later why that's the case, because most of our running times for solving linear systems comes from matrix factorizations. Matrix factorizations for sparse matrices, they use a bunch of pivoting strategies to try to get the sparsity in a nice structure. And how expensive those pivoting strategies run is, it's kind of like a combinatorial step, and it's hard to characterize. So in practice, it can be much, much cheaper than n cubed. Writing it down on paper, exact worst-case flop counts, unless you have a nice structure, it's hard to say. Okay, with a direct method like a matrix factorization. For a banded matrix, that's a very nice form of a sparse matrix. It's exactly nk squared flops. So that's the order, I should say. It's known to be nk squared flops. For an orthogonal matrix, inverting the matrix, so solving the linear system, is the same as multiplying by the transpose. Right? That's a consequence of having orthonormal columns. So it's just back to matrix vector multiplication, order n squared. And for permutation, we might think about it as somehow being linear, but it costs 0 flops as per the strict definition of flops. So let's talk about matrix factorizations, which I think historically have been more the focus in numerical methods, and they're more kind of like the standard of what you'd learn when you talk about numerical linear algebra. So you've probably learned, I would assume, that you can solve a linear system by Gaussian elimination. It's a very kind of intuitive method that many people encounter in let's say, previous courses. More typically, it's useful instead to factorize a matrix to solve a linear system. Gaussian elimination is intuitive, but it has numerical problems in practice, so it's essentially never used. Matrix factorizations are much more stable, and it doesn't gain you anything in terms of computation. So using matrix factorization is both more stable and it's as expensive. So it's I think just somehow a method that people think about in principle but don't apply. So the typical approach, which is done when you call, by the way, a\b, it's done for you behind the scenes, is to factorize your matrix into a product of other matrices. So I'm going to write it as a1 times ak. And typically k is 2 or 3. So the decompositions you'll learn today, they all have k equals 2. But k equals 3 is also common. Let's say the SVD is an example of k equals 3. But something called the LDL transpose factorization is common as well. It's like a generalization of the Cholesky when you have rank deficiency. So we'll just talk about the most basic ones, which involve k equals 2. But you first factor your matrix as a product of matrices, and then each of these by construction are invertible. And so to solve ax equals b, okay, we can actually solve for a linear system in A1, then a linear system in A2, all the way through a linear system in AK, and that gives us the answer. And why is this a good idea? Well, computing the factorization itself is typically expensive, so it's as expensive as solving a linear system. It's going to be in the order of n cubed. So it's not going to save us computation time, that step. Applying the factorization, so once we've computed these, is by construction always going to be cheaper. So it's going to be done, it's going to be possible in n squared flops. Why is that? That's because each of these are going to be computed as special matrices, either orthogonal, diagonal, lower triangular, or upper triangular, or permutation as well, is something we also throw into the mix. And we know that all of those have cheap costs in terms of solving linear systems from what we went through. Right, so diagonal is the cheapest, but the other ones are order n squared. So just maybe to say it once more, the purpose of the matrix factorization is to express the matrix as a product of simpler matrices, each of which is cheaper in terms of solving a linear system in that matrix. And after we've done so, then we can actually use them to solve the original system of linear equations via this, something like this. Okay, so that is the kind of standard, I'd say, in numerical linear algebra, matrix factorizations. It has more of the focus than indirect methods, which we'll talk about at the end. And it's also very useful if you have situations in which you're solving many linear systems in the same matrix. So let's suppose I was going to solve ax equals b, ax equals c, ax equals d, etc. Then I can compute a matrix factorization once, right, which is going to be on the order of n cubed. And I can apply it 3 times, which is on the order of n squared each time, in order to solve the linear system. Because now if I'm going to be solving, let's say, the linear system in B, I'm just applying the factorization, it's n squared. The linear system in C, I'm applying it again, it's n squared. And in D, it's n squared again. So in MATLAB, if you, for example, do a matrix B, where you are asking to solve a linear system in every column of the matrix B, then it computes the matrix factorization once of A, and then it applies it for every column. So it does so intelligently. Right? The naive way would be, here it would be 3n cubed. Or if this had, let's say p columns, it would be pn cubed rather than n cubed plus pn squared. So it's a big difference if you're going to be solving many linear systems in the same matrix. Any questions before we move on to the specifics? Okay, so my personal favorite, I don't know why I like the QR decomposition so much, I just do, is the QR decomposition. And it has a bad name because it's just named after the letters used in the decomposition, but I think it's a beautiful method. So if you have an m by n matrix where the matrix is tall, so m is bigger than or equal to n, any such matrix has the QR decomposition. And actually, if the matrix has full column rank, the QR decomposition is unique. So there's exactly one way to write this. Where Q is an orthogonal matrix, it's m by n, where the columns are orthonormal. So that means it satisfies Q transpose Q equals the identity. And R is upper triangular. Okay, that's the structure for a QR decomposition. And you can compute this, let's say I'm talking about a square matrix. So this is actually n by n in something a little cheaper than 2 times n times 2n cubed flops. Okay, and there are various ways to do this. I reference a book at the end of the the lecture notes in the references section. It's a book by Golub and Van Loan called Matrix Computations. I think it's a wonderful book for all of this, and it explains to you various ways to do this. So you can use something called Givens rotations, householder transformations. That's at least the two most common ways to compute QR decompositions, and they all lead to running times that are essentially on the order of like a little cheaper than 2n cubed. One property of a QR decomposition is that the number of non-zero elements on the diagonal of R exactly corresponds to the rank of A. So if A had full column rank, if A had rank n, then all of the elements on the diagonal of R will be non-zero. And in that case, the columns of Q span the column space of A. Okay, so Q transpose, once I compute a QR decomposition, Q transpose is the projector onto the column space of A. It's the projection matrix on the column space of A. So if A is non-singular and it's square, right? So QR decompositions are actually a bit more general because they apply to tall matrices. But in the case we want to actually solve a linear system, so A is back to being square and non-singular. We can solve AX equals B with a QR in two steps. The first is that we multiply. Okay, we have this linear system AX equals B. We write this as QRX equals B. We multiply both sides by Q transpose. We get R times X equals Q transpose B. Okay, that costs order n squared because I multiplied by it's a matrix vector product. And now this is an upper triangular system, right? I have R times X equals something, some vector, and R looks like this. So solving this, getting X equals R inverse Q transpose B is again n squared. Okay, so that's the explanation for why applying the QR after you've computed the QR to solve a linear system costs order n squared. Any questions? Okay. QR's like best friend is the Cholesky decomposition. So these are the two most basic matrix factorizations. Cholesky is more specialized. Okay, it applies to a smaller set of matrices than QR. We're not even talking about square matrices. Cholesky requires an STD matrix, not STD, excuse me, a PSD matrix, positive semi-definite matrix, or as in the form I've written it for you, a positive definite matrix. Okay, so one that's that has the lowest eigenvalue strictly larger than 0. So if I have such a matrix A, okay, it's symmetric and it has the lowest eigenvalue strictly larger than 0, then it has a unique Cholesky decomposition. I can write it as L times L transpose, where L is lower triangular. Okay, so L transpose will look like this, and L transpose will look like this, upper triangular. So I can write it as a product of two such matrices. And you can compute this in n cubed on the order of n cubed flops. So it's in terms of, let's say, exact flop counts, it's a bit cheaper than a QR decomposition. It's n cubed over 3. I claim you could also compute a Cholesky from a QR, but that would just be silly. Why could you compute a Cholesky from a QR? So let's suppose I told you that A was B transpose B. I gave you that form of A. It's symmetric and it's positive definite, so I can write it like this. And I computed a QR of B. Then B transpose B is R transpose QR, right? But Q is orthogonal by construction, so this is just R transpose R. And I can just call, for example, R transpose L, right? R is upper triangular, R transpose is lower triangular, so I could just, for example, define L to be R transpose, and that would give me a Cholesky. So if I wanted to, and I could, and I had a factored form of A like this, because it's PSD or PD, I could compute a QR and it would give me a Cholesky, but that's not an efficient method. I just wanted to somehow relate the two for you in that way. Okay, so just like we could solve a linear system with the QR decomposition, we can also solve it with the Cholesky. How do we do so? We essentially just use our forward and back substitution methods that we learned, right? So I write down, oh, I'm actually out of paper. I guess I'll do the back. Actually, let me grab some paper. Oh, you have some. Thank you. Okay, so if I have a system like this, right, I have ax equals b, I have a Cholesky factorization, I have a linear system like this, then let's say I first call this y, and I solve the system Ly equals b. And I can do this, so I can compute this in n squared. This is forward substitution. Right? And now I have this linear system to solve, L transpose x equals y, right? Because I still don't have the solution x. And I can do that by back substitution. So that's the explanation for why, after I've computed the Cholesky, it just costs n squared, on the order of n squared flops, to solve a linear system. Okay, so computing the QR and computing the Cholesky, that is a complicated, those are complicated things to learn. Okay, it is very seldom that you would write your own code for QR or for Cholesky, and it's usually a mistake. If you're doing that, you've probably gone too far. I would say, talk to your friend, have your friend talk you out of it. It's not a good idea to write your own QR or Cholesky factorization code. Thankfully, LAPOC is available to everybody. It's free. It's very fast. That code has been highly optimized. So where these numbers come from may be a bit mysterious, but if you want to look at the Golub and Van Loan book, you'll see some nice explanations of that. After you have them computed, which you can compute them in like essentially any programming language, solving linear systems is very straightforward. It's just what we explained here, okay, with either of them. And solving many linear systems in a row is also relatively cheap. It's just the number of linear systems you want to solve times n squared. So an important extension of the Cholesky is the Cholesky for a matrix that's banded with a bandwidth k. And in that case, computing a Cholesky takes only on the order of nk squared flops, and solving only takes on the order of nk flops. So if I have a constant bandwidth, if I have a big matrix with a bandwidth of like 5 or something small, then both computing the Cholesky and solving the linear system in the Cholesky is on the order of n flops. So it's linear. It's much, much cheaper than n cubed. You can also use the QR for banded systems. The numbers, it would still be order n. It's just this happens to be the more common route that people think about. Okay. So unless there are questions, I'm going to move on to least squares problems. So least squares problems, right? Every time we talk about linear regression, or really anytime we talk about any quadratic minimization, hiding underneath is the linear system that we want to solve. Right? Minimizing a quadratic, if I take the gradient set it equal to 0, that's a linear system in the Hessian that I want to solve. And for the least squares problem, right, that linear system is this guy. Sometimes it's called the normal equations. At least that's what people call this in numerical methods. Okay, so a question could be, how can we use Cholesky and QR to solve a linear system of this form in order to perform linear regression? So we're going to assume that x has full column rank, so this is non-singular. Otherwise, this discussion, we have to modify it in order to make sense, right? So we'll assume x transpose x is invertible. How do I solve this linear system with Cholesky? Well, I've broken it down here for you. Computing x transpose y, okay, it's a matrix vector multiplication, cost in the order of n times p. computing x transpose x costs on the order of np squared. So that's already going to be as expensive as the dominant step in this computation, just taking the sample covariance, x transpose x. Computing the Cholesky of x transpose x costs p cubed, on the order of p cubed. That's what we learned. And solving the linear system after you've computed the Cholesky costs in the order of p squared. Okay, so if n is large in comparison to p, because let's say we have lots of samples, we're performing a linear regression on fewer features, the most dominant cost in this sequence of steps is just computing x transpose x. Computing the Cholesky of x transpose x itself is cheaper. But if n and p are comparable, then they're about the same. So the total cost is about n times p squared plus p cubed. Or if n is much bigger, then it's just np squared, and the cost is dominated by the second step here. Okay. How about the same problem, but using a QR decomposition? So there's a key identity that we use in order to perform least squares minimization with QR, and that's this one. So let's suppose I give you the Q from QR, and I form another matrix Q tilde. So let's suppose this is n m by n. Do I have? No, I didn't use. I used the least squares notation here. This is going to be n by p. Okay, and let's suppose that this is n by n minus p, and this is also orthogonal, and it completes the basis. Meaning that if I look at the columns of Q and the columns of Q tilde, that gives me a basis for all of Rn. Okay, and they're all orthogonal. So if I define this matrix P, which is Q and then Q tilde stacked in the columns, this is an orthogonal matrix. And it's n by n. Okay, so we don't actually need to compute such a Q tilde. We just need to kind of use it to convince ourselves of a particular equality. And that's this equality. If I look at the, let's say, 2 norm of x squared, okay, I claim that's the same as the 2 norm of p transpose x squared. So if p is orthogonal, so is p transpose. And orthogonal matrices preserve the 2 norm. Okay, if you're not convinced of that, just multiply this out. Write this as x transpose p times p transpose x, and then you'll see that p times p transpose is identity by orthogonality. And okay, this is actually, by definition of our Q and Q tilde, it's on the first bunch of rows, it's Q transpose times x, and then on the bunch of rows below that, it's Q tilde transpose times x. So I can write that as Q transpose x 2 norm squared plus Q tilde transpose x 2 norm squared. Okay, so this is all we really wanted to arrive at, is that if I have, let's say, matrices Q and Q tilde that are mutually orthogonal, I can write the 2 norm squared of any vector x as the 2 norm of Q transpose x squared plus the 2 norm of Q tilde transpose x squared. So let's apply this now. Apply this to x equals y minus x beta. And write x equals QR as a QR decomposition. Then I can write the criterion of the least squares problem, right? This criterion, as Q transpose y minus, I'm going to substitute in now QR beta. I'm substituting in for x QR plus, okay, Q tilde transpose y minus QR beta squared. Okay, I'm just applying this identity that we derived to the residual y minus x beta. So the criterion of the least squares problem I can write like this. The first term here I can multiply through by Q transpose, and I just get Q transpose y minus r times beta squared. And the second term I can multiply through by Q tilde transpose, and I just get Q tilde transpose y squared. So what happened to Q tilde times the second term? q tilde times transpose q is 0 because they have orthogonal columns. And here we use the fact that q transpose q is identity to write this just as r times beta. Okay, so in other words, we've just proved that reducing or minimizing the least squares loss over beta is the same as minimizing the sum of these two squared losses over beta. But this one's a constant, doesn't depend on beta. So with respect to minimizing over beta, we can just throw it away. We don't care about it. So our goal is now to minimize this over beta. And R is, it's a square upper triangular matrix. And we can exactly solve for beta. We can set R beta equals Q transpose Y. We can make this equal to 0 and hence minimize it by solving for beta in this linear system. Okay, and solving this costs n squared. It's just back substitution. So let's recap. We had to compute the QR decomposition. That was n times p squared, a little cheaper than that. We had to compute the inner product of q transpose y. That was just np. And we had to solve this linear system, right? R beta equals q transpose y. And that just cost, beta is, of course, p-dimensional, p squared, by back substitution. Was there a question somewhere? Yeah.
When you speak of normal x, you're just using the factor language you tilde are orthogonal to each other as well, or just split. I'm just missing that.
Here?
Yeah.
No, they don't need to be orthogonal at this point. I mean, p needs to be orthogonal. Here I'm just writing this as, one big vector, q transpose x, q tilde transpose x. The L2 norm of this vector is just the sum of squares of all the components, and I can split it up into this and that. That's it. Any other questions?
How we went from when we were splitting up y minus x beta squared, y the second term above is equal to the second term below. Is that because the q tilde?
Yes, that's right. Yeah. So I multiply q tilde transpose q, I get 0 because all the columns of q tilde and q are orthogonal. That's right. Okay, so I'm going to try to compare these for you. So why we would use QR versus Cholesky. It's a hard thing to do because it's not an easy answer. But in order to try to answer it, we're going to learn about sensitivity, a concept called sensitivity analysis. So I guess I'm going to try to keep this somewhat maybe high level because this is not a pivotal thing for you guys to learn in the context of an optimization course, but I think it's interesting. Let's suppose that I'm asking you to solve a linear system in a matrix A, like this one, Ax equals B. Okay, and A was close to a singular matrix. So A was not itself singular, but it was close to a singular matrix. And the way I'm defining that is I'm saying that actually the distance between A and the set of rank k matrices, let's say for some k less than n, is small. So it's close to some rank k matrix and operator norm. So this script Rk is a set of all matrices B whose rank is k, and this distance is just the smallest I can make the operator norm of A minus B over all such matrices B. If that's small, so we can maybe develop a bit more with the SVD for you to see why this is the case, but if that's small, then it's going to be hard to solve a linear system in A. It's going to be numerically difficult. And in fact, you can precisely quantify this distance. I think this is kind of a simple and elegant way of expressing it. The distance between A and the space of rank k matrices is exactly the k plus first singular value of A. So if I were to order the singular values in decreasing order, after I take the SVD of A, if the k plus first singular value is 0, that means that all of the singular values after that are 0, and that means that A is exactly rank k, right? Because only the first k are non-zero. If the k plus first singular value is small, you can kind of think it's close to a rank k matrix, and that's exactly what this equality is telling you. So actually, the distance in operator norm to the space of rank k matrices is exactly sigma k plus 1. Okay, and essentially, all I'm trying to say here is that we have to pay attention to such things practically in programmatic implementations when we're solving linear systems. Because if we have a small, like let's suppose that A was close to a low-rank matrix, then it's going to be hard to compute QR factorizations or Cholesky factorizations accurately and solve linear systems in them reliably. So, right, so here's a basic result. The proof's on the next slide. I'm going to skip the proof because I don't think it's important. But here's a basic result that's supposed to motivate kind of the idea of being close to low rankedness and how difficult that could propagate into how the solution might depend on that perturbation. So let's suppose I'm looking to solve a linear system in the matrix A. So I'm trying to solve AX equals B. But I'm going to look at a perturbed system. So I'm going to actually change the matrix A by adding a small amount epsilon times the matrix F. I'm going to change the vector B by adding a small amount epsilon times the vector F. Okay, and we're going to ask, how different can the solutions be when epsilon is 0 and epsilon is some small fixed number? And you can imagine I can move towards the space of low-ranked matrices in some way by adding a perturbation here. This is supposed to be motivating such sensitivity. And let's denote the solution to the perturbed system. So when I change A to A plus epsilon F, and I change B to B plus epsilon F, let's denote the solution by x of epsilon. Okay, and the solution to the original problem, x of 0, I'm just going to call x. So here's a kind of classic theorem, and I put the proof on the next slide. The solution to a perturbed system like this one, okay, satisfies the following bound in terms of relative distance to x. So the x is the solution to the system when epsilon is 0, our original system ax equals b. The norm of x of epsilon minus x squared divided by the norm of x, this should say the norm of x squared. Oh, no, sorry. There should be no square in the top. I should just say the distance between x of epsilon and x in L2 norm divided by the norm L2 norm of x is less than or equal to kappa, which I'll explain what that is in a second, times something you can view as a constant plus order epsilon squared. Kappa is the condition number of A. So it's the ratio of the largest to the smallest singular values of A. So that means the poorer conditioned the matrix is, okay, let's say the closer it is to a low-rank matrix, or the more elliptical the contours are of the Hessian, right? The bigger the ratio of the largest eigenvalue to the smallest eigenvalue, or largest singular value to smallest singular value, the worse it is essentially numerically for you if you just have small perturbations in A or in the output in the target vector B, right? Because that somehow affects this bound on the right-hand side in a large way. Okay, so I guess the takeaway is that if you have a poorly conditioned matrix and you have a small numerical precision error, that could propagate quite a bit into the solution. So if I actually somehow calculated the QR factorization slightly wrong, so I'm not actually really solving a linear system in A, because I have some small rounding error. If the matrix was poorly conditioned in the first place, then that can have a big effect on the solution itself. And the proof is quite simple. It just uses Taylor series. So let's now use this to address the question of Cholesky versus least squares. Cholesky versus QR for something like least squares. Cholesky, essentially, remember, it applies directly to x transpose x. So first, it's expensive to compute that. It's expensive just to compute this outer product. But even worse off is that somehow we pay, in terms of conditioning, we pay for the condition number of x transpose x, in terms of the sensitivity analysis we just did, which is the condition number of x itself squared. Okay? If I took the SVD of x transpose x, then the singular values are the squares of those of x. That's why this is the case. QR operates directly on x, right? We took a QR of x itself. I never formed x transpose x. That was kind of the entire point of this decomposition. So we could modify the least squares loss and just take a QR of x itself. And so in terms of conditioning, we only pay for the condition number of x itself. Okay, you can show that the sensitivity essentially scales with kappa of x. So the high-level summary is that Cholesky uses less memory, and if you look at actually the flop count, it's a little bit cheaper, but the QR is more stable. So if you have like a least square system where, let's say, there's lots of correlations among the columns, so it's not like a nice design for any reason, then you can expect the QR to be more stable because it essentially only scales with the condition number of x, not the condition number of x squared. And every time you call a backslash b in MATLAB, or you solve a least squares problem in really any programming language that's intelligent in terms of its usage of numerical linear methods, it guesses whether it should be using Cholesky or QR based on a bunch of heuristics. Okay, it'll perform a bunch of heuristic checks, and it'll choose one of them, and it'll use that matrix factorization, trying to balance kind of stability with memory and speed. And if I'm remembering correctly, I think MATLAB has a propensity for using QRs much more often. So I think some of MATLAB's flowchart, if you look at it, if I'm not mistaken, it tends to rely on QR much more often. It likes to side in that direction. Okay, so I think that's a good spot to take a break. And let's take a quick break, and we'll come back and discuss indirect methods. I guess a little bit more I want to cover. Let's just jump right back in. So far, up until this point in the lecture, we've been talking about direct methods for linear systems. These are non-iterative methods. So the idea is that you perform some kind of factorization, like a QR, like this. Okay, there's some algorithm that's required for that, but this does not have an iterative nature in the sense that it's not seeking to get something closer and closer to a QR. It computes a QR in a fixed number of iterations, and that's what determines this cost. Once you have the QR, okay, then you do things like matrix multiplication and back substitution. Again, we're not kind of iterating towards a solution. We're not getting closer and closer to a solution. We have a fixed number of iterations that we apply to get the exact solution. So on a perfect, like say, a computing environment, so there's no issues of numerical precision errors. We don't worry about that at all. Direct methods give you the exact solution. So there is, in principle, they give you like the exact solution to a linear system. The counterpart to a direct method is an indirect method, which is more aligned with everything you've learned so far in the course. These are methods that produce a sequence of estimates, or iterates. We call them xk, just like we could think about with all of our methods so far, that will converge to a solution as k goes to infinity. They are most often used for very large and sparse systems. So everything you've learned so far in the course for optimization, gradient descent, through proximal Newton, these are all iterative methods. They are not exact. They don't give you the exact solution on a perfect computing environment and any finite number of iterations in general. The only exception that we very briefly talked about, I just mentioned it, was the simplex algorithm. It is an indirect, non-iterative, it's a direct, non-iterative method for linear programs. But like everything, let's say, you've learned so far, think about it as being iterative or indirect. So when should we use direct versus indirect? I had put this in the slides to remind myself that I wanted to pull a quote from Tim Davis, and I forgot, so all you have is his name. I guess that means you should go ask him. So Tim Davis is he's a CS professor at University of Florida, if I'm remembering correctly, and he's written the majority of code for sparse matrix factorizations. So he has a C package called SweetSparse that says a bunch of sparse matrix factorizations like sparse Cholesky and sparse QR. If you call a backslash b in MATLAB, it is Tim's code that gets called. MATLAB, it's open source sparse QR code that MATLAB uses if you have a sparse matrix generically. So he knows what he's talking about. He writes nice code. And he had a quote that I'll just kind of try to recreate it, but I'll put it in the notes once I find it. It said something like, if you have a matrix that you can fit easily in memory, so you don't have to worry about kind of jockeying it to get into memory, then you should always use direct methods. There's no point in using indirect methods. The kind of start of when you should consider an indirect method is when you have a big enough matrix that like just getting into memory is an issue. Okay, so at that scale, you should start thinking about indirect methods. Hopefully that's helpful. So direct methods have a nice kind of, just like there's a bunch of people who write books and spend their whole lives like studying direct methods, the same can be said for indirect methods. It's a very rich literature. And arguably the two most basic methods for indirect methods for linear systems date back well before matrix factorizations, and they're due to Jacobi and Gauss. So Jacobi iterations and Gauss-Seidel iterations are the two most basic indirect or iterative methods for solving a linear system. And we'll see them again next week, not next week, on Wednesday actually, when we talk about coordinate descent, because there I'll explain to you that they are exactly coordinate descent for solving a particular optimization problem, and that's this problem. So if this is my function, f of x, x transpose ax minus b transpose x, I guess I have to divide this one by 2. Then minimizing f of x, let's say a is positive definite, is equivalent to setting the gradient equal to 0, right, which is equivalent to solving ax equals b. So solving this linear system is the same as minimizing this quadratic. If I were to perform coordinate descent, so I were to optimize out over x1, then over x2, then over x3, etc., that is exactly it's either one flavor or the other, depending on whether or not I use the most recent information or not. So in Jacobi iterations, I perform all of these coordinate updates at the same time. Okay, and I never use recent information. So after I, let's say, solve for xn, I solve for x1 through xn, but I just always use the old versions of x1 through xn from the last cycle. So if I were to optimize this out over, let's say, xi, set it to minimize it exactly, I would get this update. Gauss-Seidel is similar, but I think about going through x1 through xn, let's say, sequentially, and always using the most recent information. So if I optimize out over x1, in the optimization for x2, I use the most recent value of x1. In the optimization for x3, I use the most recent values for x1 and x2, and so forth. That is the only difference between Gauss-Seidel and Jacobi, but it's a huge difference. It's actually like, it makes all the difference because Jacobi iterations generically do not converge, so they only converge kind of under nice situations, whereas Gauss-Seidel iterations always converge. And that's actually kind of bad news for parallelization because these are trivially parallelized. Right? I can do these all in parallel, and these are not. So this, for a long time, kind of was a topic that people were thinking about. How can we get something like Jacobi to converge that's parallel? That I won't talk about now, but I just wanted to kind of point out these are the two most basic iterative approaches. Okay, so how about, I'm going to do an example at the end that compares them so you can see them. How about gradient descent? So we have this criterion. I guess in the slides I called it phi. We learned gradient descent as the kind of the first method. Why don't we just apply it to this criterion in order to solve the linear system? Right, the gradient descent steps are going to be kind of cheap. They're going to be on the order of n squared because I have to do matrix multiplication. That's it. And so if I can afford less than n iterations and get to a pretty good solution, I'll be cheaper than n cubed. Seems like a reasonable thing to try. And so gradient descent for this problem, right, just moves in the direction of t times the negative gradient. And the negative gradient is just b minus ax. That's it. So think about, or it's actually ax minus b. So the negative gradient is, I don't know, I'm confusing myself so much. The gradient is ax minus b. The negative gradient is b minus ax. So we're moving in the direction of the negative gradient. So that's x plus t times this residual. Okay, this is an interesting case where we can do exact step size optimization. So we can actually look in the direction r that we're trying to traverse with gradient descent, and we can find the step size t that minimizes this quadratic exactly. So back when I talked about gradient descent, I said this was never a good idea unless you had quadratics, which was kind of at the time maybe seemed like a very weird special case, but now we're in this weird special case. And we can do exact step size optimization. And so it turns out that the best step size to take is exactly this one. You can see it's dependent on the kind of iteration itself. It's r transpose r divided by r transpose ar, where r is just the current residual, b minus ax. Okay, so that's the step size I'm going to use here. I'm just going to apply gradient descent. So what can we say about it? Well, we already know, let's say, hopefully you guys remember this much, that this is strongly convex. It's a quadratic, and I told you A was positive definite, and it has some smallest eigenvalue. It's strongly convex, so we should expect a linear convergence rate. This should converge quickly like log of 1 over epsilon. Okay, and in fact, with this specific problem, which is just solving a linear system with gradient descent, we can say a much more precise result in terms of the contraction factor, and that is this one. Okay, so from one iteration to the next, if I look at the a-norm distance between xk and the solution, which I'm calling x, it decreases from the previous iteration by an amount square root of 1 minus the condition number to the minus 1. So square root of 1 minus 1 over the condition number. Okay, so we can again see that somehow conditioning, the more poorly conditioned the system, the slower this is going to converge. So the proof is similar to what we did for strong convexity. I think we did that on the homework. This proof is actually much easier. It's just direct calculation. And an important note is that the contraction factor here depends adversely on the condition number, as we already said. And it turns out that in order to get an epsilon multiplicatively suboptimal solution, so if I wanted to get an epsilon suboptimal solution in this sense, so I wanted to get something that was epsilon times as bad where I begun, then I require log of 1 over epsilon iterations, but the constant here scales linearly with the condition number of A. So it's in the order of kappa times log of 1 over epsilon. So if the ratio of the largest to smallest singular values is large, let's say it's in the thousands, this multiplies this cost by a lot. So for poorly conditioned linear systems, order kappa log 1 over epsilon could be actually a lot of iterations because kappa could be very large. Okay, now comes in conjugate gradient, which is a rich enough method we could do a whole lecture on it, but I'm just going to cover it in 5 minutes because we covered QR and Cholesky and everything else in this lecture as well. So what is the problem with gradient descent? If kappa is large, okay, then the contours of this function, f, they're like these really elongated ellipsoids. That's what that means. And gradient descent, roughly speaking, is going to spend a lot of time traversing back and forth kind of in these directions across the valley. Okay, it's going to be moving orthogonal, so the gradient points are orthogonal to the contours. And for most iterations, we're going to be pointing ourselves somehow in a direction like this. And if that's the solution, we're going to be spending too much time moving orthogonal to the contours and getting pushed somehow back and forth across the valley like this. Now, another way to see that is that actually there's not enough diversity in these directions r. So I'm going to be computing these directions rk minus 1, which is b minus axk minus 1. I'm going to be looking to move in the direction r at every iteration. I'm going to take some step size t times r and move in that direction. There's not enough diversity. They're all pointing kind of in the same directions because of how kind of strongly elliptical this is, how far from spherical these contours are. So conjugate gradient is, I think it's an extremely clever idea, and the purpose of it is to do something like gradient descent, so to repeat iterations like this one, but to use different directions p that are constructed to be diverse. They're not going to be pointing in the kind of same direction or in similar directions iteration to iteration. They're constructed to be diverse so that we can overcome poor conditioning like this. In the case of poor conditioning, we can be making progress iteration to iteration rather than undoing progress like we are here. Okay, and the original construction and the typical construction for conjugate gradient is that I choose the direction p at the kth iteration to be orthogonal to all of the previous k minus 1 directions after I multiply by a. Okay, so this, you can already see somehow that we're getting diversity here. I've moved in directions p1 through pk minus 1 in the past k minus 1 iterations. I'm going to be trying to make pk far from those. So specifically, this says I'm going to make pk orthogonal to a times p1 through a times pk minus 1. And they satisfy something called a conjugacy. That's where the name conjugate gradient comes from. It's a fancy name to say that if I say that p and q are a conjugate, it's just a fancy way of saying that p transpose aq is 0. So I conjugate, if I is identity, is just what you know as orthogonal. And a conjugate is, for a positive definite matrix, is just it's orthogonal in a different coordinate system. That's all it is. Okay, so I'm saying p has to be orthogonal to p1 through pk minus 1 in this different coordinate system where I've rotated by a. And I say that, with respect to this notation, now p is said to be a conjugate with each of the previous directions. Okay, so here's how we proceed. Here's the intuition. If I were to fix a direction p, and I were to try to do the step size optimization, it turns out that I can again get the exactly optimal step size because phi is a quadratic. So if you're at the point x, and you're trying to move in the direction p, and you ask what is the best t I can take, then the answer is p transpose r over p transpose ap, where r is b minus ax. Okay, so if I were to then take this optimal step size, and I were to look at moving in some direction p, I guess here I called it pk, then, and I were to plug that into the criterion itself, so I were to evaluate my quadratic itself, so a pretty simple calculation brings you to the criterion at iteration k is equal to the criterion at iteration k minus 1 minus a bunch of stuff, or really just one fraction, and that is 1/2 times p transpose r divided by p transpose ap. So now we see that there's kind of two conflicting goals in conjugate gradient. The one is we want our directions to be a conjugate. We want diversity, right? Because we want to avoid this kind of behavior. We want diversity. So that means we want the new direction to be different from the old ones. The other kind of conflicting goal is that we want p to be somewhat aligned with r, which is a step we would have taken in gradient descent. If it wasn't, then this would be small. And so what you're going to see is that you decrease the criterion very little. So we have to be somewhat aligned with r in order to make a decent decrease on the criterion. So it turns out you can meet these two considerations simultaneously, and I'm skipping some of the details, but the Galb and Van Loan book gives a really nice treatment of this. By choosing to update p in a very simple way based on the last iteration. So if I have pk minus 1, and I have rk minus 1, okay, this is the residual b minus ax. This is my previous conjugate gradient direction. Okay, I can very simply take a linear combination of the two. I can take r plus beta k times pk minus 1, where beta k is equal to this guy here, minus p transpose ar over minus p transpose ap, but that's the old p, pk minus 1. And if you just multiply, let's say, both sides here by pk minus 1 transpose a, you'll see that actually you get 0 on the right-hand side. It's constructed to be 0, so that this is exactly a conjugate with pk minus 1, and all the previous directions as well. Okay, so the algorithm itself is very simple. We just essentially move in some direction, and we update the directions to move in based on this form. So it's like the residual, like we use in gradient descent, but it's adding a bit of our previous direction as well. So that's all of conjugate gradient. So what is the convergence analysis for conjugate gradient? The convergence analysis, maybe surprisingly, maybe not, depending on maybe how much you've seen of this, is much, much harder. So like analyzing conjugate gradient is something that people have actually found different and new proofs just in recent years that invoke Chebyshev polynomials and kind of lead to other interesting algorithms. So it's a classic topic, but the analysis is a very kind of intricate and interesting task. And what you end up is again, linear conversions. But the most important thing to remember, if you all remembered between gradient descent and conjugate gradient after this lecture, is how the final iteration complexity depends on the condition number. So for gradient descent, we had on the order of kappa times log of 1 over epsilon. And for conjugate gradient, we have in the order of square root of kappa times log of 1 over epsilon. So it has a much better dependence on kappa. So for really poorly conditioned systems, the difference between kappa and square root of kappa can be a very big deal. And we see in practice that conjugate gradient performs much, much better. Okay. So I just cooked up this example. I wanted to give you an example. And this was not a poorly conditioned system, by the way. This was, I took standard Gaussian entries for my feature matrix in least squares. So I just solved, I just minimized the least squares problem of this form, right? Y minus x beta, which means I had myself solving a linear system of this form. And I took just IID normal 0, 1 entries for x, so it was not poorly conditioned at all. I wasn't constructing it to be. And I ran Jacobi, Gauss-Seidel, gradient descent, and conjugate gradient. And as I'll explain a bit more next time when we talk about coordinate descent, and we'll dive into methods like Jacobi and Gauss-Seidel, it's fair to compare the iterations here because they all have the same cost. So every iteration of every method costs order NP. So by iteration for coordinate descent, I mean, for Gauss-Seidel, for example, I mean one full pass over x1 or over beta 1 through beta p. It just costs order NP. And one iteration of gradient descent or conjugate gradient costs, again, just order NP. So it's really fair to compare them. And here's what it looks like. So actually, I solved 100 least squares problems, and I just plotted all the results. Each time I generated x to have IID normal 0, 1 entries. And Jacobi is lying up here in black, so it's not converging. It's just hovering up here at some large positive number. That's the suboptimality gap. Gradient descent is here in green. So the average is in darker green. You probably can't see it on the projector, but you can see it if you look at the slides. I drew the average and as a dark, thick line. Gauss-Seidel and conjugate gradient have similar and interestingly similar behaviors. So they both converge a lot faster than conjugate gradient, than gradient descent. And this is not even for a particularly poorly conditioned problem. For a poorly conditioned problem, it would be a much bigger difference. And it looks like conjugate gradient is actually doing a bit better for most of the problems than Gauss-Seidel. Okay, one of the strengths of Gauss-Seidel, which we'll see next time, is that it's just coordinate descent. So it actually applies to a bunch of other problems, not just linear systems. Whereas conjugate gradient is kind of a fairly specific idea to linear systems. So this should maybe motivate us to better study coordinate descent, which we'll do next time. I put some advanced topics here. In case you're interested, there's some keywords. You can come talk to me about them. And yeah, that was our numerical linear algebra whirlwind. So I will see you guys on Wednesday.